Hey nerds, welcome. Today we are diving into 7 exciting and challenging quizzes on arrays. The questions are based on real world insights and get ready to test your skills. Let me know how many you got right. So let's begin with the first one, 2 longest sessions. Here you are tasked with analyzing user activity on a social media platform. You have an array of integers representing user sessions. Here is your array. Each value is the duration of the session in minutes. So which algorithm would you use to find the 2 longest sessions in a single traversal? A. Sort the array and pick the last 2 elements. B. Use 2 variables to track the largest and second largest sessions. C. Use a min heap to track the top 2 sessions. Or D. Traverse the array twice to find the 2 largest values. I'll give you 10 seconds to think about it. You may pause the video if you need more time. Well, the correct answer is B. Use 2 variables to track the largest and second largest session. Let's see how so. Here is the given array 120, 45, 60, 90 and 30. So we have 2 variables initialized to minus infinity. And as we traverse the array, we update those variables. If they are greater than the values, then we update the variables. So this approach takes order of n time and order of 1 space complexity. So that is why this is the most efficient solution. But let's see why the other options are incorrect. Starting with option A, sort the array and pick the last 2 elements. So after sorting, this is what the array looks like, and the last 2 elements are basically the largest and second largest. Although this gives the correct answer to us, but sorting the array itself takes order of n log n time. So this is not the most efficient solution. Option C, use a min heap to track the top 2 sessions. So here we have a min heap with maximum of 2 elements, and so as we traverse the array, we update the min heap. So here, as you see, 60 is greater than 45, so we replace 60 with 45, and 90 replaces 60. And when we reach the end of the array, we have the largest and second largest values. This also gives us the correct answer, the right answer, but it takes order of n log k time. Just imagine if we had to find the top k sessions, then would this be the efficient solution? Option D, traverse the array twice to find the 2 largest values. So as we traverse the array, we first find the largest value, and second time when we traverse the array, we find the second largest value. This approach takes order of 2n, which simplifies to order of n time complexity. This is correct as well as efficient algorithm, but it requires 2 passes. So for single pass, option B is the right answer. Quiz 2, array of response times. You are managing a server log represented as an array of response time. So here's the array, and these are the response times. Your task is to find the response time that occurs the most frequently. So if you see the array, 200 occurs 3 times, which is the most frequent. Which approach is most efficient to find this most frequent occurrence? A. Use a nested loop to count occurrences of each response time. B. Sort the array and count occurrences in one pass. C. Use a hash map to store frequencies of each response time. Or D. Create a new array to store counts of each unique response time. So you have 10 seconds to think about it. The correct option is C. Use a hash map to store frequencies of each response time. So here's the array, and as you traverse to the array, create a hash map and update the value in their corresponding frequencies. So as you traverse the array, you see you can update the frequencies of the elements. And at the end of the array, you can figure out which is the most occurring value in the hash map. So this solution is optimal for counting frequencies in large datasets. Let's see why other options are incorrect. A. Use a nested loop to count occurrences of each response time. A nested loop approach compares each element with all other elements in the array to count occurrences. So this is order of n squared term complexity. So for really large data sets, this is very inefficient and impractical in real world scenarios. Option B, sort the array and count occurrences in one pass. So this sorting itself takes order of n log n time, which is slower than order of n. Option D, create a new array to store counts of each unique response time. But to implement this approach, you need to first identify unique elements, which involves traversing and sorting the array. This adds unnecessary complexity, and space complexity increases as you create an additional array. Quiz 3, Identical Shopping Carts. Here, your e-commerce platform needs to quickly identify whether two users have identical shopping carts, and the carts are represented by arrays with item IDs. How would you determine if the two arrays are identical? A. Compare the arrays element by element. B. Sort both arrays and compare them. C. Use a hash map to count occurrences of each item in both arrays. D. Use nested loops to compare each item in one array with every item in the other. We'll wait for 10 seconds and let's see the answer. So the right answer is B. Sort both arrays and compare them. So here are our cards. These are the two arrays representing the item IDs in our cards. So after sorting, this is how the arrays look. Visualizing it, we can say that they are very much identical. So here we compare index by index. So if each of the values in the indexes of the two arrays are identical, then we say that the cards are same. Otherwise, they are not. So sorting takes order of n log n time and comparison is order of n. So basically it's order of n log n solution. This is effective for simpler and small arrays like cards. Now let's see why answer A is incorrect. Comparing array element by element. So if we directly compare without sorting them, then we can say that we just say that they are not identical, even though logically they are identical. Option C, use a hash map to count occurrences of each item in both arrays. A hash map can be used to store the frequency. So if the same items can be added in multiple frequencies, then we can use a hash map. But this is a very simple card, so we do not actually need a hash map here. So this approach is more complex than simply sorting, basically. This works well for larger datasets. Incorrect answer D. Use nested loops to compare each item in one array with every item in the other. This approach is highly inefficient because the time complexity is order of n squared, and it's impractical for larger arrays for real-world applications. Quiz 4. Find the missing number. You are given an array containing n-1 integers, where the integers are in the range 1 to n with no duplicate. One number is missing from the array. So if you see the example array, we have 1, 2, 4, 6, 5. So obviously 3 is missing. How would you efficiently find the missing number? A. Sort the array and iterate to find the missing number. B. Use a hash map to track the presence of numbers. C. Calculate the sum of 1 to n and subtract the sum of array elements. Or D. Use nested loops to compare the array with the full range. So we'll wait for 10 seconds for you to think. The right answer is C. Calculate the sum of 1 to n and subtract the sum of array elements. So this is the array as you see 1, 2, 4, 6, 5. So the sum is 18. And sum of first n numbers as we know is n into n plus 1 by 2, which comes to 21. So the result is 21 minus 18, which is 3. So the time complexity here is order of n and space complexity is order of 1. Why option A is incorrect is because the sorting itself takes order of n log n time complexity. So this is not the efficient solution for that. Option B is incorrect because a hash map can be used to track which numbers from 1 to n are present in the array. The missing number is the one not found in the hash map. While this approach works in order of n time, but it requires order of n additional space as well for the hash map. Option D, use nested loops to compare the array with the full range. Nested loops, as we know, introduce a time complexity of order of n squared, which is highly inefficient compared to other operators and impractical for larger arrays. Quiz 5. Rotate the array. You are given an array 1, 2, 3, 4, 5 and an integer k equals 2, representing the number of positions to rotate the array to the right. So after rotation, you can see that it becomes 4, 5, 1, 2, 3. So here we are rotating the array 2 times. First time the value 5 comes to the index 0 and the second time value 4 comes to index 0, shifting the other elements. So what is the most efficient way to perform this rotation? A. Use nested loops to shift elements one at a time. B. Use an auxiliary array to store the rotated result. C. Reverse parts of the array and then reverse the entire array. Or D. Append the array to itself and extract the rotated segment. So let's wait for 10 seconds for you to think. The right answer is C. Reverse parts of the array and then reverse the entire array. So if you reverse the last k elements, which is last 2 elements, the array becomes 1, 2, 3, 5, 4. And then reverse the first n minus k elements. The first 3 elements, if you reverse, it becomes 3, 2, 1, 5, 4. Now reverse the entire array. It becomes 4, 5, 1, 2, 3. This is what we expect the result to be. This takes time, order of n time complexity and no extra additional space required. Let's see why option A is incorrect, using nested loops to shift the elements one at a time. This approach requires shifting elements one by one for k position, which means it's order of k by n time complexity. This is highly inefficient for large arrays. Computationally, it's expensive, even though it is correct. Let's see why option B is incorrect, using an auxiliary array to store the rotated result. So while this method works in order of n time, it requires order of n additional space for auxiliary array. So this violates space efficiency requirements for in-place array manipulation. Option D, append the array to itself and extract the rotated segment. So this method is memory intensive. This works, but it's memory intensive and it requires order of 2n space to store the appended array. So after appending the same array to itself, the new array becomes 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now you can extract the segment from index n minus k, which means we get 4, 5, 1, 2, 3. This is the right answer. This is correct solution, but it requires order of 2n space. Quiz 6, a pair with the target sum. So here is an array 1, 4, 7, 12, 15 and the target sum s, which is 19. Determine if there is a pair of elements in the array that adds up to s. What is the most efficient approach? A. Use nested loops to check all pairs. B. Sort the array and use a two-pointer approach. C. Use a hash map to track complements. Or D. Create a cumulative sum array and search for the pair. We'll wait for 10 seconds. Well, the right option is C. Use a hash map to track complements. So here's the array 1, 4, 7, 12, 15. And as we traverse through the array, we initialize a hash map and store those elements into the hash map. So 1. Since 1 is not present in the hash map, we put in the sum minus the value, which is 19 minus 1, into the hash map, 18, and value is the index 0. 4 is not present in the hash map, so we put 19 minus 4, which is 15, and value 1. 7 is not present in the hash map, so we put 19 minus 7, 12, and at index 2. As we traverse to 12, we see that 12 is present in the hash map, which means a complement target sum pair is present in the array. Each lookup in the hash map takes order of 1 time complexity and traversing the array is order of n. Space complexity is order of n for the hash map. Let's see why option A is incorrect. Use nested loop to check all pairs. This approach has a time complexity of order of n squared. This is a brute force approach, so it is not the most efficient solution for us and inefficient for larger arrays specifically. Option B, sort the array and use two-pointer approach. After sorting two pointers, left and right, can be used to traverse the array. Adjust the pointers based on whether their sum is less than or greater than the target. Sorting the array requires order of n log n time, which adds unnecessary overhead. But if the array was already sorted, then this becomes a very good solution for us, which would be order of n solution for us. Option D, create a cumulative sum array and search for the pair. This approach is unnecessarily complex for this problem, and constructing the cumulative sum array itself takes order of n time, but searching for the pair introduces order of n squared in the worst case scenario. Final quiz, merge two sorted arrays. So we have two sorted arrays, 135 and 246. Your task is to merge these two arrays into a single sorted array efficiently. So what approach should we use? A, concatenate the two arrays and solve the result. B, create a hash map to store all elements and extract the sorted result. C, use nested loops to insert elements of array 2 into array 1. Or D, use two pointers to merge the arrays. So we'll wait for 10 seconds for you to think. The right answer is D. Use two pointers to merge the arrays. So here are our two sorted arrays, 135 and 246. So this is our resultant array. We have the result array of length of array 1 plus length of array 2. And we have two indexes pointing to index 0 of each of the arrays. So we see whichever is the smallest of the two and add it to the result array. So from 1 and 2, 1 is smallest. So we add 1 to the result array and update the indexes accordingly. Out of 2 and 3, 2 is smaller, so we add 2. And 3, 4, 3 is smaller, and so on. So as we go to the end of the array, we have our sorted resultant array. So the time complexity here is order of m plus n. M is length of array 1 and n is length of array 2. Space complexity is order of m plus n as well. This is for the result array. Let's see why option A is incorrect. Concatenate the two arrays and sort the result. Concatenating the arrays and sorting them ensures the final result is sorted. This is a probable solution, but it's not just efficient as the previous one. It takes order of n plus n log n plus n. This is for the sorting. This is less efficient than the two-pointer approach. Option B, create a hash map to store all elements and extract the sorted result. Hash maps are unnecessary for this problem, and constructing the hash map adds overhead. Sorting the keys is again order of k log k. Option C, use nested loop to insert elements of array 2 into array 1. This approach has a time complexity of order of m into n, making it inefficient for large arrays. The insertion operation also involves shifting elements into array 1, adding further overhead. So let's see what the key takeaways for today are. Efficient solutions often rely on optimized data structures like hash maps, heaps, and algorithms like two-pointer approaches. Understanding problem constraints like space and time complexity are crucial, and input properties and edge cases are very crucial for choosing the right approach. Arrays are versatile for solving problems like searching, sorting, and data manipulation. So test yourself, try solving more array problems to solidify your understanding. Also, let me know how many you got right and ask your friends how many they got right. Let me know if you want me to add more quizzes on arrays. And if you are new here, please consider subscribing and liking here. And thank you. Thank you for your patience.